The next speaker is Max Kurze, and so there is a title here, and I briefly saw an interesting alternate title, and I'll let Max give the talk.
All right, thanks for the introduction. As you might guess from the title, I'm going today basically report on my experience on working with intrinsically typed languages in Rocq. And right, there's another title. If that doesn't say anything to you, then you should just think of this talk as giving you a guide on how you can abuse Roqq's type checker to do some type checking of your own DSLs. Okay, so consider the small example. It's just a simple expression over bit vectors. And what we would like to do is we would like to be able to make sure that certain subterms here actually have the same type. For example, because this addition over bit vectors is just defined on bit vectors that actually have the same length. Or we would actually also like to be sure that all the variable references are actually scoped correctly. But before we can get into that interesting stuff, we first have to define this language. And we define this language in a deeply embedded style, like you've seen it probably thousands of times. We just have an inductive, call that action here, but just expressions. And then we have one constructor for each of our language constructs. So we have constants, as you've already seen, but just imagine there may also be not only these bit vector literals, but there may be structs or enums or whatever. So we're a bit more general here. Then we have variables and we have binders. And then to have some more interesting operations, we also have addition over bit vectors and we have concatenation. Now, in order to do anything at all with Roqq's type checker, we first of all need to encode the necessary information for that in some type in Rocq. So if we want to do the type checking of our DSL here with the type checker of Rocq, we first of all have to encode all the typing rules, the whole type system basically, in the dependent types of this AST. So what we're going to do is we're going to add a new type parameter here, and then we're going to define for each of our language constructs which type it returns. So for the constants, that's just the type of the value. For the variable, we might ignore that for the moment. For the binder, we just forward the type of the body as the type of the whole construct. And then for the addition, we would like to be a bit more specific. So for the addition, we only define this to be well defined if we have two operands that are actually bit vectors and they have to have the same length. And then for the concatenation, they actually might have a different length, but then the return type will actually have their combined length. And now, to also resolve the variable case, we introduce another type argument, and that's, we call it a variable context, but it's just a list of all the identifiers that are currently in scope together with the type that has been bound to the identifier. So for the variable, what we will then do, we just take this variable context from the type level and we force each variable reference to carry a proof that its identifier is actually part of that context. And then we can simply take the type that has been in the context and use that as the type of our variable reference statement. And the other place where the variable context gets interesting is in the binding construct. There we will again take it from the type, and now we will add the newly bound identifier to it before we push it into the body, or in the subterm that we call body. In all other places, we just simply take always the context from the type level and push it in all to the subterms without any modification. Okay, so now that's our language. Let's have a look at a couple of examples. The first example is just simple addition over bit vectors. There's no problem at all. Rocq simply type checks this term, but I would actually like to emphasize what it means. That does not only mean that this term is well defined, like the AST is well defined with regard to Roqq's type system, but it also means that the type of our DSL that is represented by this AST is actually well typed with regard to our previously defined type system, the one I've just seen on the last slide. All right. A second example involving a binder that we'll also go through immediately without any modifications. And once we have a third example that also has a variable reference, we will actually notice the first problem, because Rocq is not able to infer automatically this kind of proof that the variable reference or the identifier A is actually part. of the variable context. So we need to help Rocq a little here by providing a tactic that would just resolve this proof. And once we provide the tactic, that example actually works out. Fine. So far, so good. Now, if we just take the exact same example and only modify it slightly by adding another binder that's not even used, it's just there, we actually reach another problem. But this time, the error message is a bit more weird, or it's a bit harder to understand, because this time Rocq actually complains that it's not able to unify the type that it inferred for the variable reference with the type that it was expecting there. And in order to find out how it came to this error, how that happened to be, we have to have a closer look at how Rocq type checks this term. All right, so here you can see the same term again, just spread out a bit into a tree-like structure. And now I will actually go through step by step on how Rocq traverses this term in order to figure out if it actually type checks or if it doesn't. And Rocq does this in a bottom-up fashion. So you can think of it like Rocq basically starts at the uppermost term and it first traverses into the leftmost subterm until it reaches the leaf basically, and then it will try to infer the type of this leaf on its own without considering any of the environment. So in this case, for the constant, it will figure out that it has no knowledge whatsoever about the variable context, but it knows that the return type here is bit vector of length 2. And only after that, Rocq will actually check if the type that it inferred matches the type that it was expecting on the one level higher, the argument of the bind here. In this case, they just unify, everything works out, and Rocq can continue. We'll then continue to again traverse this tree until it reaches the leftmost subterm, the next one, and infer the type of the second constant, which is again similar as the first one, only that this time it's bits of length 3. And then Rocq will unify the type that it inferred, again with the type that it was expecting. Works out again. And now we will eventually reach the variable reference, where it will not really work out because during the inference of the variable reference, the L tag will actually be triggered. And now the L tag sees as a goal that it should just prove that A is somewhere in this extension variable. And what the tactic will obviously do will just apply ineq and basically resolve our variable reference in something that is not really compatible with the type that we're expecting here. And so it happened to be that these types are resolved to some types that are incompatible, and we cannot make progress anymore at this point. Right. Now, that's a bit of a bummer. Let's take a step back and try to figure out what we would have wanted instead to happen. What we intended to have here is we would have wanted that the variable context is taken from the top level type annotation, and it should be traversed, or it should be passed downwards through the AST, starting at the top and then just propagating downwards, adding all the variable identifiers. So logically, conceptually, the variable references or the variable context should be propagated top down, while the type checking actually happens bottom up. So there's some kind of misalignment there. And the key insight of our paper was that you can effectively reverse the type checking order of Rocq by using bidirectionality hints. So what we are doing is replace these bidirectionality hints in front of all the arguments for our constructors. There's actually one line missing. We also do that for the const case. So also for the constants, we do the same kind of bidirectionality hint. And what then happens is the following. Let's do the type checking again. We again start at the outermost term. But this time, we do not directly traverse into the subterms, but we will first, because of the bidirectionality hint, we will force to first unify with the expectation that we have of the type annotation. Right. And only afterwards, we will actually traverse into the first subterm, where again the same thing happens. We will not directly infer the type of this term, but we will first have to unify with the expectation. Right? So we basically propagate the variable context and only then the type inference happens. Same thing for the second subterm, so the inner bind will also first hit the bidirectionality hint. So we'll first propagate our variable context. So at this point, the A is actually properly propagated here, and only then the type checking will continue with the subterms. So we just type the const on the left, and then once we reach the variable reference, now the actually important point here is that the bidirectionality hint is in front of our argument h. So what will happen is the bidirectionality hint forces the unification with the expected type, which will propagate the variable context, and then only afterwards the L tag will be triggered and the L tag will be able to construct the proof that we wanted. All right, so now we use bidirectionality hints and everything worked out. Now we were actually able to type check this term and to make sure that all the valuable references in this term are actually correctly scoped. So you might not be excited, you want to go out there, implement this for your own languages, and you will hit certain problems where there were certain terms that actually worked before, but now once we have the bidirectionality hints, they stopped working. And that's because it turns out that it's actually quite nice to do the return type unification and inference in a bottom-up manner instead of the top-down manner that we now have for the variable context. So what we actually propose in this paper is to re-reverse the type checking order such that we have two passes. We have a first pass that goes top-down, propagates all the variable context, and then we have a second pass that goes bottom-up again and does all the inference and the unification of the return types for a DSL. But if you're interested in that, then you should definitely read the paper and check out the tutorial that we published. Thanks for your attention.
So just a quick question with respect to the bidirectionality hints. So if I define a Rocq function manipulating the AST, do I also need to add hints?
Yeah.
And well, what if I define...
Depends. Yeah. Really depends. If it just wraps... basically, if you're just doing all that stuff, generating the necessary NST, and then you apply it to function, that's totally fine. If you want to apply the function more inside of the AST, then you also have to provide the hints, because then the top level annotation is outside of your function and needs to be propagated through it.
Okay, and what if I define a recursive function? How do you type check the body? Does it work out? Did you try something like this? Or?
How do you mean that?
Because I imagine you can only, I mean, I've never used hints myself, but I imagine you can only add the hints after defining a function. Is that the case?
That's fine.
Yeah, but then does it work out, type checking the body of the function?
Oh, that's a good question.
Okay, maybe you can talk about it later.
I'm not sure about that.
Yeah, maybe let's take that one offline.
Yeah.
Was there another? Yes.
So last year, someone wrote an explanation for the documentation about bidirectional hints. Maybe that's you. I don't know who's behind the pseudo. And we were basically like looking, wow, that's great. That's how it works. What would be an example of that? So if you have a tutorial, that would be great merging into documentation, because it sounds like a great example of bidirectional hints in real life.
That seems like a really nice idea.
So I didn't quite understand in the end. Maybe you could get us a little spoiler for the rest of the paper. So did you manage to actually make it so that this also works and type checks in current Rocq, or do you more have like a proposal for how Rocq could be extended to make both of them work?
No, it works.
Okay.
We're using basically, there are two approaches on how this can be done. One is, I have a backup slide for that. So one is you can write a wrapper where you're basically deferring the unification of these return types. That way it can work, but you can also get rid of the wrapper and implement it in LTAG2 using the pretype function. Yeah.
Okay, thanks.
Okay, I think we should thank Max now.